All right, so let's begin here. Suppose that you know the eigenvalues and eigenvectors of 1, 2, 3, 4, 1, 2, 4, 3 matrices are these two things. Okay? I want to show you how diagonalizations work. So you first have to know what these eigenvalues, eigenvectors mean. So remember that definition of eigenvectors, eigenvalue means that AV equals to lambda V. So V is an eigenvector if it's non-zero and satisfies such an equation for some value lambda. Okay? So in the case of lambda equals to 5 and eigenvector 1, 2, this is what it means. It's 1, 2, 4, 3, and then 1, 2 would be equal to 5 times 1, 2. And then this next one would be 1, 2, 4, 3 times 1, negative 1 gives you negative 1 times 1, 2. Which is, you have 5, 10 here. This will be negative 1, negative 2. Yes?
How come for negative 1 it's times 1, 2? Shouldn't it be 1, negative 1?
Oh, sorry. Should be 1 negative. You're right. Right. Now I'm right. Okay. Thank you. So now I can put those two things together. Right. 1, 2, 4, 3 times 1, 2, 1, negative 1. Okay. Think about what goes here in the first column. What goes here and here? 1, 2, 1, 2 is what? 5, isn't it? 4 times 1, 3 times 2, added, what do you get? 10. It's exactly this one. Right? What goes here then? This. Okay. Is it okay? So the first thing to note is that if you have matrix multiplication results column-wise like that, you can put the columns next to each other, and then the result of a matrix times bunch of columns is the same thing with columns. Okay. Now, another thing that we want to do is there's a way to represent this as this times something. It's 1, 2, 1, negative 1. And see the difference? Here I have matrix A times the column of vectors, right? Columns, a bunch of columns. Now I put the columns first, and I'm writing something down here. And the numbers that you put here would be 5, 0, 0, negative 1. Okay. And what you see is that 5 and negative 1 are indeed the eigenvalues. Do you agree? These are indeed eigenvalues. And then we're almost there. So the way we are going to name this is we're going to name this vector as P. This vector we decide to call it as A, right? And this is P. And now this is a diagonal matrix, so we put D for diagonal. Okay. And the simple scheme that we can express what we obtain is this. It's AP equals to P times diagonal. Right? Now, I want to get rid of P. How do I get rid of P? there's no division. Instead, you multiply by the inverse, right? So you multiply P inverse both sides, and you have to be careful. If you want to get rid of the P on the left side, you have to multiply P inverse on the left side. See, matrices are not commutative. These two certainly don't commute. You can check that they don't commute. So it's important that you multiply P inverse on the left side. If you're multiplying P inverse on the left side, you better do the same thing on this side as well. So these cancel, and now you have P inverse AP equals to the diagonal matrix, and that's called the diagonalization of A. Okay, so
So then A would be equal to D, right?
the P inverse AP would be equal to D. So the result that we just obtained is that 1, 1, 2, negative 1 inverse times the matrix 1, 2, 4, 3 times 1, 1, 2, negative 1 is the diagonal matrix of the eigenvalues. Okay? And this is called diagonalization.